Hello, today we have this faulty 386 motherboard. The date code visible on the PCB points to October 92 as the production date. It has two-part chipset and fixed 50 MHz oscillator, which will allow only for CPUs up to 25 MHz. Appropriate CPU here would be a 25 MHz 386DX. It will also take an optional FPU and 30-pin memory modules. A nice compact board with not many configuration options. There are practically no jumpers here other than for external devices as speaker, LEDs or buttons. On the retro web, I was able to find one similar board with this chipset, a data expert board, but it's only similar in layout. There are substantial differences in the position and presence of some chips on these boards. Still similar though. Maybe mine is some copy or a board derived from the data expert one, or maybe vice versa. This board had a usual problem with a leaking battery, as it damaged part of the PCB around the place where the battery was soldered in, but there is no visible damage to the thin traces around the area. I think these traces still look intact and should be okay, but you never know what can hide under all these connectors and parts. The acid still could penetrate and affect some of the neighboring chips or other parts, or could corrode traces under some of the mounted components. This motherboard, after it was removed from the computer, had to be stored under a stack of other junk, as many of the through-hole components have bent pins, as if the board would be pressed against something hard with a lot of force. Some of these can be bent so much that they probably can tear through the solder mask lacquer and cause shorts to neighboring traces or other pins. So I will have to work for some time to unbend all these pins which look like they are shorted. As if there were not enough mishaps already, someone who removed the PGA CPU from the socket broke the socket itself and drove a screwdriver into the board, damaging a few traces and possibly even some internal layers. I have repaired the three visible broken traces and can only hope that the internal layers were not affected. Let's take a little closer look at this broken and abused board. As I mentioned, we have a fixed 50 MHz oscillator, which in more modern boards would be replaced by a PLL synthesized generator with an adjustable clock speeds. Here we can at least put a 66 MHz oscillator and have a 33 MHz CPU instead of a 25 MHz one, as hinted by a PCB marking. We have two chipset parts, OPTI82C496, which is a DRAM controller, 80 bus controller, controls the CPU, data bus, ROM shadowing and some other stuff, and SIS85C206, which does IRQ, DMA transfers and timers. Only thing I know about this board is that it does not start up, does not post, it just does completely nothing. Before we will try to power it up, let's check if the power rails are not shorted. Okay, now let's try to power this thing up and check it with a thermal camera to see if there are no components which would get very hot, which could indicate some internal shorts or similar problems. So I see temperatures seem to be around from 20 something to 30 something degrees. So I think there are no visible problems with too hot components here. Okay, now let's put the post-test card into the ISA slot and let's try to power the board up with the card inserted. No CPU for now. I'm only interested if there will be all necessary power LEDs and a proper reset signal. As we can see, the reset does not seem to be active. It should blink for a split second after the power up. So I have started to look for some other obvious problems which I could spot easily, and I have found that the CMOS reset jumper is on the reset position. Let's switch it back to a normal state and let's try again. Okay, now we see the reset LED blinking just after the power up, so the board is trying to reset non-existing CPU. Let's put the CPU in and try with it. And as advertised, it just does completely nothing. No postcodes, no any other activity. Completely dead. So I'm wondering if the CPU is actually being reset properly. The part issuing reset signals is the large Opti chipset part 82496, for which I was luckily able to find a datasheet on bitsavers.org. There are two different reset signals: sys-RST line resetting ISA devices, DMA and keyboard controllers, and a separate CPU reset line. I want to check if this CPU reset is actually happening properly. So I will take the CPU out of the socket and just check with a multimeter. So just after powering the board up, we could see that there was a brief high signal which transitioned back to low. So this seems to be working correctly. Now I would like to check both 50 MHz and 14 MHz generators to see if they are providing stable and correct frequencies to the board. So both clocks seem to be stable and correct. What to do now? I would like to take a look at the block diagram of the system, which is included in the datasheet for the chipset. Our board has to follow this block diagram. So we can say that this is really a block diagram of our board. A backbone of most computer systems will be data and address buses. In this architecture, all data transfers between external devices and the CPU are mediated by our Opti chipset part. Data bus has front system bus side which connects CPU to chipset, and a system part, XD lines, which connects chipset to external devices as DMA, keyboard, BIOS and ISA bus through additional buffers. The chipset is doing transfer, synchronization and other magic, some of which we will try to understand later. The address bus, on the other hand, is not really translated or mediated in any way. The system address bus takes 16 bits from 32-bit CPU address bus and connects them through additional buffers to external devices. It would be good to be able to see if the CPU is showing any signs of activity. After the reset, it should enter reset vector address on address lines and start execution from this place. I would assume that this address would be a ROM address from which execution of BIOS should start. The ROM is easy to clip on to see activity of both data and address system buses, and I can use a clip which I have designed and built to do that. Awesome! So to acquire and analyze bus activity, I will use my U3 Pro 32 logic analyzer, a dip clip which I have designed, and a connector with a harness which I have also designed for my U3 Pro 32. This is a 2mm pitch connector in 3D printed casing, with a bunch of single pin connectors soldered onto connector pins. Simple but very useful solution to a cable mess when you try to analyze a lot of digital lines at the same time. So we will tap to the BIOS chip and connect almost all digital lines to the analyzer. I will omit a chip enable line as it seems to be simply tied to the ground. To see and analyze the bus activity, we will use DSView application bundled with the analyzer. The rest of this video will be basically analyzing and trying to understand what is happening on the system buses and trying to draw some conclusions from it. The analyzer has two modes: stream mode, where acquired data is being sent immediately to the application through the USB 3.0 port in the analyzer, and a buffer mode, where analyzer writes acquired data to the internal DRAM buffer. A CPU bus of the system can reach a 50 MHz as the system oscillator. I want to be able to acquire data at least 100 MHz acquisition speed. In stream mode, I can have 30 channels working at 100 MHz. Let's try that option and see what we will be able to get. 100 MHz acquisition speed, 5 seconds of acquisition, and let's start the analyzer. Now I will power up the board and let's see what we will get. And that is what I've got from this first try. There's clearly some digital activity happening on both system buses, the address and the data one. At the very beginning we see a series of pulses on some of the lines, which do not look like a proper digital activity, but then it seems that a proper digital activity starts. This looks like an actual transactions on the bus. Reads, writes, something. To make any sense of all this digital activity, first I would like to name all of the used analyzer inputs with pin IDs of the chip we are clipped onto. This will make it much easier to understand what is going on. You can look at all these signals with the ability to differentiate between the address bus activity and data bus activity. Let's look at the very first proper digital transaction that we can see on the bus, just after these pulses that we saw. Right away we can see an interesting pattern on the address lines from A0 to A3. It clearly looks like there is an incremented address entered on these lines. You can see bit 0 alternating between zeros and ones, effectively producing even and odd numbers, and the lines from A1 to A3 also alternating between zeros and ones with increased period of 2 cycles of the previous line. This is clearly a 4-bit number increased by 1 every bus cycle. And this is clearly a good sign of something, probably CPU, trying to read from certain memory location. To make even more sense of the recorded activity, we need to somehow convert bus states to bits and assemble bits into values. This is where the decoders built into the analyzer application will come in handy. To convert digital states to bits and then assemble binary numbers, we have to use numbers and state decoder from DSView. This decoder allows to choose some of analyzer inputs and build a digital number out of bits represented by these lines. There is only one requirement. We need to provide a clock signal to trigger the decoder at the desired points in time. First thing which came to my mind was to tap to the 50 MHz system clock to trigger the decoder. I have soldered additional wire to the output of 50 MHz oscillator, and I will connect that to the first 3 input of the analyzer. Now we can try to acquire data from the buses once again and see if we will have the clock. Great! Now we have clock signal to trigger the decoders. Or do we? The acquired clock signal does not look stable. There are many gaps in the capture and sometimes clock stops entirely on few milliseconds, which is not acceptable as at this time decoders would not be triggered. I'm guessing that it's not a problem of a clock itself, but rather acquisition settings. What can we tweak to improve acquisition? To sample more than 30 channels with a frequency greater than 100 MHz, we have to switch to buffer mode. where we can have all 32 channels sampled at 250 MHz. With buffer compression turned on, we can theoretically catch a nice long chunk of the bus signals. Let's try that. Now in buffer mode, with a 250 MHz sample frequency, the gaps vanished and the clock seems to be more or less stable. It's now good enough to trigger the decoders. It seems that 100 MHz was just not fast enough to properly acquire 50 MHz clock, even if according to the Nyquist-Shannon theorem, it should be enough to sample signal of a given frequency f with a frequency of 2f. Maybe it's some problem of the stream mode? USB 3.0 not pushing the data fast enough at 100 MHz? Okay, let's leave that for now and let's move on with troubleshooting of our board. Now we can at last configure the decoders and see what is really happening on the data and address buses. First decoder for address bus is starting its work. We can see a new line which appeared at the top of the window where the decoded values will be, and the decoding progress on the right panel. Okay, we finally have some real data to look at. At the top of the window we can see decoded addresses entered on the bus by CPU at subsequent bus cycles. What we can tell from this decode? We definitely can see that addresses are entered in groups of 4, and also clearly see that this is the ROM being read, as the active low output enable line of the ROM BIOS chip is going low during these 3 groups of 4 addresses. It's clear that the CPU is reading 3 groups of 4 bytes from ROM, 12 bytes in total. Does this combination of 12 bytes in 3 groups of 4 should tell us something? Yes, it seems to be a rather typical behavior of a 386DX CPU instruction prefetch unit, which reads instructions in 4-byte blocks, filling in the 12-byte instruction prefetch queue. This queue was originally designed as 16 bytes long one, but Intel had to abandon 16-byte length and use only 12 bytes due to known instruction pipelining bug. What else we can see here? When capture is zoomed out, it looks like this first group of addresses and the data got from the ROM is repeating many times, just as the CPU is constantly trying to read the same group of bytes, and for some reason it repeats the same read again and again. This does not look like a normal behavior, but let's investigate further without drawing conclusions too early. Let's see what addresses are entered on the address bus during this repeated read. First address is 7FF0 hex. It is similar to the reset vector of the 386 CPU, but altered on the most significant bit. Proper reset vector should be FFF0. At first I thought that maybe something on the board does address remapping or something like this. But the address bus is not altered by any logic in any way, as we saw previously. It is only buffered between a CPU side and the system side. It turned out that my address bus decoder was misconfigured, and it did not decode most significant bit properly. So the real address entered on the bus was a proper FFF0, not 7FF0. But we will have to live with 7FF0, as I have discovered the decoder configuration mistake long after shooting the footage for the video. So we have 12 consecutive bytes being read from ROM at the reset vector address FFF0. Let's try to decode what is being read from this address. I'm assuming that this should be a block of x86 assembly instructions with operands. Let's try to use some quick online disassembly tool to see if we will be able to decode the data to proper x86 assembly. First 5 bytes decoded to a long jump instruction with a 16-bit operand of a segment F000 and 16-bit offset address of E05B in the segment. Rest of the bytes are not interesting, as after long jump, CPU would not execute them, so we can discard that part. The long jump is a proper instruction which we would expect here. BIOS is pointing the CPU to the initialization code located at E05B, which fits in the address space of a 64K ROM chip. CPU should alter IP register, that is instruction pointer register, effectively making it jump to the address, and start execution from this place by doing prefetch of a 12 bytes from address E05B. But instead it is reading the same block of assembly from FFF0 again and again. So everything points to a proper first initialization step, which is repeating over and over again without a success. I would assume that the address bus is working correctly, as we see proper addresses on the bus and the proper data being output from the ROM. But for some reason this data does not seem to reach the CPU, as it is never trying to execute instructions being successfully output by the ROM chip. So again, we see the proper address reach the ROM and the ROM outputting proper data, but it does not seem to reach the CPU. I'm wondering how the data looks on the CPU data bus side. I will connect the analyzer directly to the CPU data bus and compare first 4 bits of this bus with first 4 bits of the system data bus. Why only 4 bits? I'm getting short on analyzer inputs, so 4 bits will have to do for now. And here we have the capture from both buses. We can compare first 4 bits of both system and data bus. We already know what is on the system bus. On the CPU side, there is some digital signal, but it's not the same signal as on corresponding bits from a system bus at the same points in time. What is happening here? I'm guessing that maybe something is wrong with the bus synchronization between the chipset and the CPU. I want to see if this repeating read pattern is caused by the CPU being constantly reset by the chipset. And maybe also start looking at data bus synchronization between the CPU and the chipset. So let's add 2 more control lines connected between the chipset and the CPU. CPU reset line, controlled by the chipset side, and the read-write line, controlled by a CPU, indicating read or write bus cycle. Okay, this does not look good. Just look at how active the reset line controlled by the chipset is. The series of initial pulses on some of the bus lines are clearly caused by constant CPU resets coming from the chipset. That may be a normal startup procedure, but later, when we saw a series of repeated initial 12-byte reads from ROM, the reset line is still very active, resetting the CPU again and again. This would explain why it is trying to start from the reset vector again and again, right? Let's look at the conditions for the CPU RST line activity described in the chipset datasheet. CPU RST is following the sysRST, and sysRST is dependent on power good signal state. PWRGD line, that is. As the datasheet states, PWRGD line should be low for normal operation of the system. So let's go down that path and check the state of PWRGD line. That is a power good line, let's say. Let's not forget that area of power connector where PWRGD signal is originated from could be affected by a battery acid. So let's take a look at the state of this line when the system is being powered up. It transitions from low to high and stays there. It's not what the datasheet tells that it should be, right? We see that the chipset is resetting the CPU again and again. Can this incorrect state be the reason? Let's see where PWRGD signal is routed to from the chipset input. It is not directly connected to power supply power good line, but that would be obvious as this line will be high for our normal operation, and datasheet is specifying explicitly low state for normal operation. I'm wondering if there is some corrosion damage near the power connector. The power good line is a thin trace coming out of the power connector and vanishing under the keyboard controller chip socket. Could it be that corrosion got somewhere under there and corroded this trace away? I have to try and track this trace to see where it is exactly going. So I have removed the keyboard controller, and under there we have yet another one sneaky 74 series chip. The trace visible here under the socket is not the one we are looking for. Could it be that power good is connected to the 7407 chip? Yes, power good seems to be going into that 7407, which is 6 line buffers with an open collector output. Convinced by the chipset datasheet, I was absolutely sure that this has to be an inverting buffer, as that it's what would be only logical explanation, right? Power good from the power supply delivers signal high. Chipset, according to the datasheet, needs a low state for normal operation, so this has to invert the power good to comply with chipset requirements, right? Let's check the behavior of the output of 7407 gate, which is connected directly to the chipset PWRGD input. It is behaving exactly in the opposite way as what the chipset datasheet tells us it should. It's low just after the power on, and then it transitions to high and stays there. So I was absolutely sure that I have found the problem. I haven't even checked the 7407 datasheet to check the truth table. After replacing the chip, there was absolutely no improvement. And only then I have checked the datasheet for 7407 and learned that this is not an inverting buffer, but a straight one, outputting the same state as on the input. So it was behaving absolutely correctly. I have started to check and map the connections of the power good lines to understand how it is all working, and I've came up with this little schematic showing how it is all connected. The power good comes out from the power supply connector, goes into an open collector buffer, which in the low input state will pull the output to ground. In high input state, it will stay in high Z mode, effectively being neutral to the circuit. Another circuit connected to PWRGD line of the chipset is a reset circuit. When reset button is pushed, it will produce a brief transition to a low state, and then again the line will be back to a high state, as the line is pulled up to 5 volts by a 4.7K resistor. So, it is now clear that this line will never stay low in a normal state. Its normal state is high, and it will stay low only if the power good from the power supply is not present, or when the reset switch is pressed. This is the wire OR mechanism mentioned in the PWRGD line description. Normal state is enforced by a weak pull-up resistor. Low state can happen only when either one of the inputs, reset or buffered power good line that is, it's strongly pulled low. Either the statement in the datasheet is completely false, or the designers of this motherboard had their own ideas on how all this should operate. Either way, I have lost a lot of time being convinced that I have found the problem when everything in this area of the board was working as designed. What is interesting is that the other chipset part, SIS interrupt and DMA controller, is connected directly to the supply power good line. It does not trigger any resets in the system and is reset by the main opti chipset part controlled by our wire or circuit of power good signal and a reset button. Okay, so I have lost a lot of time chasing a completely made up problem, misguided by the chipset datasheet. What to do next? We have to go back to the last correct finding. We are reading far jump from ROM, but never executing it. CPU may get some data back, but maybe the data is corrupted and the resets are caused by a CPU misbehaving somehow after reading the corrupted instructions and being reset by some watchdog in the chipset. I'm suspecting some problems on a data bus between the chipset and the CPU. There are a lot of control lines between these two, and it would be good to tap to these lines to see if they are all behaving correctly. This will be a serious undertaking, as I'm not able to use a clip this time. I will have to solder a lot of wires to the bottom of PGA socket, get into a wire mess, capture the line states, and try to make some sense out of the capture. Before I will do that, I want to quickly go over all pins of our opti chipset part and see what kind of signals are on each pin. Is it a high state, a low state, or a digital waveform, or activity? So now I'm checking all of the pins and writing down their states, writing down everything on a printout of the chip pinout. I will try to compare the states with the datasheet later and see if we have an expected state or something else on each pin. So I've got to the XD lines, which are the system data bus, a very interesting area of the signals as we know. XD0 has only these very short pulses which look suspicious, but just look at XD1 line. This does not look like a proper digital signal at all. We have some strange waveform here, which would indicate that something connected to this line is seriously misbehaving. So what is connected to the 16-bit system data bus on this system? As we saw previously, we have ROM BIOS, which we know is working correctly. We have a chipset on which we have measured the distorted signal. We have a few other things like SIS chipset part. It has lower 8 bits of the bus connected for a DMA transfers. We have a keyboard controller which is pulled out currently and cannot cause problems. And ISA bus buffers, which move the data back and forth between the system bus and an ISA bus. My eyes are on 74245 ISA bus buffer, as these like to go bad, probably because some failed ISA card could damage such a buffer chip. Let's remove it and measure the XD1 line again. Unfortunately, no luck. The XD line is still distorted. Only suspicious thing left on this bus is the SIS DMA and interrupt controller. Could it cause the problem? Only way to find out is to cut the XD1 trace and see if this will impact the waveform in any way. When tracing XD1 input to the SIS chip, which is rather easy to find as there is a group of 8 lines bundled together to create lower 8 bits of a system data bus, which is an input to the chip, I have noticed that this XD1 line does not have a continuity between the opti chipset part and the SIS chipset part. These pins does not seem to be connected at all. Let's analyze the trace on the board. And hey, it looks completely intact except the part which is under the quality control sticker stick to the board. And just look at this small puncture in the sticker, which I have not noticed before. And even if I would notice it, I would never think that there can be damaged trace under it. Let's remove the sticker and check under it what is happening there. And I think we have found the probable cause of the failure. The XT1 trace is damaged by some sharp object driven into the board, making this minuscule puncture in the sticker under the board. It's quite ironic that the probable cause of a failure was hiding under the quality control sticker. Okay, let's fix this trace and let's check if this will improve things. I have fixed the trace with a piece of Kiner wire. Here it is. And yeah, I have the speaker connected, and we can now try it. Guess what? It works. It's nice. Okay, so let's put the keyboard controller back in. Let's solder this removed buffer back in. The keyboard controller is back, and this buffer for the lower 8 bits of the ISA bus is back, and we can try to turn this thing on and see if this will still beep exactly like it was beeping without these chips. Okay, so this is a classic no graphic SCART signal, I guess. Very slow. So let's maybe short the turbo, which is somewhere here. Okay, so here is the power switch, and I have shorted the turbo switch. Yep, I think we're right at home. It works. So the next thing to do is to put some video card and to take a look at this board. And then of course we will play electro body on it, just as I wanted. Great. Now that we have the board fixed and working, I want to do 2 additional activities. I want to understand why I saw this discrepancy between the system and CPU data buses. Corresponding bits on the buses had not have the same states at the same bus cycles. Why is that? I have read 386DX datasheet, and I think I know why it works like this. As we know, 386DX instruction prefetch unit reads instructions in 12-byte block of 3 4-byte double word blocks from ROM. We saw that clearly on the analyzer trace. 386DX data bus is 32-bit, while system bus is 16-bit. ROM BIOS chip itself has only 8-bit data output. So we have 3 double word reads going on a 32-bit CPU bus from an 8-bit device. And here is the probable reason for what we saw. 386DX has 4 control lines which tell the busmaster, chipset that is, where it wants to get the read operation result, BE0 to BE3. These lines are indicating where next readed byte should end up on a CPU data bus. Double word read from an 8-bit device, which is a 4-byte long read, seem to be loaded sequentially, as the RAM can output only 1 byte per bus cycle, onto the 4 groups of 32-bit CPU data bus lines. First byte on lines from 0 to 7, second one on lines from 8 to 15, and so on until entire double word fills all 32 bits of a CPU data bus. Let's confirm the theory in the real system. I have usual clip on a ROM to see what is being read from it. Additionally, I have soldered wires to the first bit of 4 8-bit groups of a CPU data bus. So this will be bits 0, 8, 15 and 24. Now we can see if the first bit of a byte being read from ROM is the same as first bit of the subsequent 8-bit groups on a CPU data bus in subsequent bus cycles. And here we have a confirmation. First bit of the readed byte is always the same as first bit of subsequent 8-bit groups in subsequent cycles, until double word is loaded onto a CPU data bus. Here we can see how changes of Q0 bit, which is bit 0 from system data bus, correspond to the changes of bits 0, 8, 15 and 24 from a CPU data bus. This is how the CPU is telling the chipset where to put the next byte while reading a double word from 8-bit RAM. First byte has bit 0 set to 0. BE0 is active at that time and byte is loaded to bits 0 to 7. Next byte has bit 0 set to 1. BE1 is active and the byte is loaded onto bits 8 till 15 of a CPU data bus, and so on. 4 bus cycles are needed to read a double word from an 8-bit RAM, obviously. It's practically impossible to compare the contents of both system and CPU buses without a mighty multiple input analyzer, which would be able to see entire CPU and system data buses at the same time. Okay, now I want to do yet another activity. In the beginning of the troubleshooting, we've done a disassembly of a first long jump instruction to check the validity of it. Now, when we have the board fixed, let's try to disassemble a bit more instructions to see what BIOS is doing during an early initialization phase. So I have dumped decoded instructions along with their ROM addresses from DSView to a text file. I could try a tool like Ghidra or some other 386 disassembler, but I just want a quick disassembly in context with some rich description of what may be happening at the early initialization phase of the system. Let's use an LLM model to disassemble and describe coherent instruction blocks, which the LLM will be able to fish out of the byte stream. So I will use Cloud AI to do the disassembly in context. I will tell it what it will deal with and ask it to fish out some interesting instruction blocks and describe them. Here, right at the beginning, we have our long jump instructing the CPU where to start initialization of the system, and bytes which I have discarded just after the jump seem to be an ASCII date of the BIOS release. Then execution of BIOS code starts after a jump. The code is disabling interrupts and checking the keyboard controller. Then the BIOS is sending value 1 to the port 80 hex, which is an address used by our post-diagnostic card. The card, if present, will store the value and display it on a 7-segment display. Then the BIOS runs some basic tests on CPU registers, setting stack pointer register with an alternate bit values 5555 and AAAA. Then AX register is being checked. Then the BIOS moves a bit pattern through all of the CPU registers, probably checking if the value will stay the same or something like that. Then it disables the NMI, non-maskable interrupt that is, outputs value 2 to the post-diagnostic port and carries on with the execution. Nice! Okay, now let's check if this board is really starting up and showing some activity with the VGA card inserted. And we can confirm repair success. The board starts up. The advanced CMOS and chipset setup is very basic here. There are not many options. Some RAM shadows, RAM wait states, ISA bus delay cycles, not much more interesting stuff. Okay, now the only thing left is to have some fun with this board. Let's play an electro body, a Polish game from the 90s on it. I remember this game well from the 90s. I have used to play the shower version a lot. Loved the music and sound effects, some of which were also used by Front 242 EBM band. So this was a long video. I wonder if anyone is still watching at this point. Thanks if you made it this far, and till the next one.